In this video, we will analyze the universal bias circuit for a BJT transistor. In this particular circuit, we have a BJT biased using what's called universal bias circuit, or sometimes voltage divider emitter stabilized circuit. In order to analyze this, we must first find the Thevenin's equivalent model by removing the transistor, shorting out the voltage supplies, and looking for the Thevenin's equivalent voltage that would appear across this set of terminals. In order to do that, then we find that RB, we'll call this RTH, and it will also be referred to as R sub B, which will be the base resistance, which is equal to R1 in parallel with R2. This is equal to, using the voltage product over the sum rule, is R1 times R2 divided by R1 plus R2, which equals 10k ohms times 5.1k ohms divided by 10k ohms plus 5.1k ohms. Substituting this in and rounding off gives us a value for RB of 3.4k ohms. Okay, so now we've got RTH. The next quantity we need is VTH. So VTH, which is also equal to, and we will call it VBB, using the voltage divider rule, equals VCC times 5 point, times R2 divided by R1 plus R2. Substituting what we know for these values, we have 12 volts times 5.1k ohms divided by 10k plus 5.1k ohms. Substituting this and rounding off gives us a value for VTH of 4.1 volts. This can be seen in this second circuit. So now we've replaced the biasing resistors with a VBB of 4.1 volts and a resistance of 3.4k ohms. The rest of the circuit, the output circuit, remains the same. RC is the same, RE is the same, and of course VCC would be the same. The next step is to find IB. IB can be determined by the equation VBB minus VBE over RB plus beta DC plus 1 times RE. Substituting in for these values, we have this is equal to 4.1 volts minus 0.7 of a volt divided by 3.4K ohms plus 100 plus 1 times 1K ohms. Simplifying, this is equal to 3.4 volts divided by 104.4 K ohms. Substituting that into the calculator, we come out with an IB of 32.6 microamps. So that solves the current in the base loop for us. The next step is to determine IC, and IC is equal to beta DC times I sub B, which is equal to 100 times 32.6 microamps. Plugging that into a calculator gives us a value for IC of 3.26 milliamps. The next step is to calculate I sub E, and that's equal to I sub B plus I sub C, which is equal to 32.6 microamps plus 3.26 milliamps. Adding those two values together gives us 3.29 milliamps. The final step is to determine VCE, and VCE is equal to VCC minus RC times IC minus RE times IE. This is equal to 12 volts minus 2K ohms times 3.26 milliamps minus 1K ohm times 3.29 milliamps. This is equal to 12 volts minus 6.52 volts minus 3.29 volts, which equals 2.19 volts. That concludes the video on the universal bias circuit.